Welcome to AI History of Western Philosophy. Today, we're diving into something I find, well, absolutely fascinating, this incredible line connecting 18th century philosophy right up to the AI in our headlines today.
It really is a remarkable thread. We're talking about the idea that our minds aren't just passively receiving information, but actively predicting and constructing our reality.
Exactly. From Immanuel Kant wrestling with the limits of reason, through neuroscience figuring out how the brain actually does this prediction stuff, the Bayesian brain idea, and landing right on, large language models.
And the key word linking all of this is prediction. It pops up everywhere. But what's maybe even more interesting and what we really want to dig into is where that prediction analogy starts to break down, especially with AI.
Right, because the differences tell us a lot. So our mission today is basically to give you a shortcut through these complex ideas. Think of it as the story of the ghost and the prediction machine.
But before we jump in, we need to state our mandatory disclaimer. It's important for you to know how we approach this material here at AI History of Western Philosophy.
Absolutely. Let's get that out there. AI-generated content, specifically this podcast, confabulates presenting ideas as fact. Though our subject is philosophy, we are not philosophers. AI History of Western Philosophy's mission, beyond pointing us to the original sources, is to experiment with philosophy as material and generate new possibilities for thought.
Okay, so with that framework in mind, our goal for you, listening, is to really grasp why wrestling with Kant, this figure from centuries ago, is still so crucial for understanding cutting-edge neuroscience and AI today. It's about seeing the architecture of thought itself.
Let's start the journey then. Back to Königsberg, 1781. Kant publishes the Critique of Pure Reason. What was the philosophical scene like? Why did he feel the need to, shake everything up?
Philosophy was kind of stuck, really, caught in a bind. On one side, you had empiricists like David Hume. Kant actually credited Hume with waking him up from his dogmatic slumber.
Hume's skepticism, right. The idea that experience is all we have, and it doesn't give us certainty about things like cause and effect.
Precisely. Hume basically said, look, you see one billiard ball hit another, and the second one moves. You see it a million times. But all you ever experience is the sequence, A, then B. You never directly perceive the necessary connection, the oomph of causation itself.
So things like causality, scientific laws, they're just habits of mind, strong correlations we get used to.
That was Hume's conclusion. And that's a huge problem if you want to do science, which relies on necessary universal laws. It basically pulls the rug out from under physics, the Enlightenment project.
Okay, so that's the skeptical ditch on one side. What was on the other?
The dogmatic slumber side, rationalists like Leibniz. They believed you could figure out deep truths about the world just by using pure reason, without necessarily needing messy sense experience. Think armchair metaphysics.
And Kant thought both were missing something fundamental.
He did. He saw Hume's skepticism as destructive and Leibniz's rationalism as unfounded. So he set himself this monumental task to prove that we can have knowledge that is both certain and necessary, yet also genuinely informative about the world.
This is where that crucial Kantian phrase comes in. Synthetic, a priori judgments. Let's unpack that because it's dense, but so important.
So a priori means knowledge that's independent of experience. It's necessary. It's universal. Like 2 + 2 is 4. You don't need to check it empirically every time.
Okay, got it. Independent of experience.
But synthetic means the knowledge actually adds something new. It synthesizes information. It's not just contained in the definition like all bachelors are unmarried. That's analytic.
Analytic is just unpacking the definition. Synthetic is adding something.
Exactly. Kant's classic example was often math or geometry. 7 + 5 is a priori. It's necessarily true. But he argued the concept 12 isn't analytically contained in 7 and 5 and plus. You have to perform a mental operation, a synthesis to get there. It tells you something new.
So Kant's project was to show how we can have these powerful synthetic a priori judgments, these necessary truths that actually structure our understanding of the world. How did he do it?
With his famous Copernican revolution in philosophy. Just like Copernicus flipped the model of the solar system, putting the sun at the center, Kant flipped the relationship between the mind and the world.
Instead of our minds conforming to objects.
Objects, as we experience them, must conform to the structure of our minds. Our cognitive faculties aren't passive receivers. They actively structure the reality we perceive.
Wow. Okay, so that immediately implies we don't see things as they really are.
That's the unavoidable consequence. It forces Kant to make this fundamental distinction between the noumenal world and the phenomenal world.
Okay, let's define those. Noumenal.
The noumenal world is the realm of things in themselves, reality, as it might exist totally independent of any observer, any mind. And Kant is adamant, this realm is fundamentally unknowable to us. We just don't have the sensory apparatus to grasp it directly. Think of it as the ultimate hidden causes behind what we sense.
So we can't know the thing in itself. What do we know then?
We know the phenomenal world. This is the world of appearances, the world as it shows up for us. And critically, it's the product of an interaction between that unknowable noumenal reality and the structuring activity of our own minds.
So experience isn't just raw data hitting us. It's data that's already been processed, shaped.
Profoundly shaped. And this shaping happens in layers. Before we can even think about an object, the raw sensory input, what Kant called the manifold of intuition, just this chaotic stream of sensation, has to be ordered.
And the first layer of ordering is built in.
Yes, the a priori forms of sensibility, space and time. Kant argues these aren't concepts we learn from experience. They are the fundamental, non-negotiable preconditions for having any experience of objects at all. They're like the built-in coordinate system of the mind.
We're just wired to perceive things as existing somewhere, and happening sequentially, time. You can't even imagine an experience outside of space and time.
Try it. It's impossible. They are the universal containers for all possible appearances. But just having data points located in space and time isn't enough to give us coherent objects that persist.
Right. You need something to bind it all together, to recognize that thing over there as, say, a cup, and the same cup I saw a moment ago.
And that's the job of the synthesis of imagination. Kant calls this a blind but indispensable function of the soul, meaning it's active, it's constructive, but it largely happens below the level of our conscious awareness. It's the engine that builds unified experience.
Our sources break the synthesis down into 3 steps. Let's walk through those. The first is about just grabbing the immediate data.
Yes, the synthesis of apprehension and intuition. This is basically gathering the scattered bits of the sensory manifold that are present right now and unifying them into a single perceptual moment, like focusing your attention and taking in the scene.
Okay, snapshot taken. But the world isn't just snapshots, things last.
Exactly. And that requires the second step, the synthesis of reproduction and imagination. This is crucial. It's the faculty that connects the perception you just had a moment ago with the one you're having now, drawing on memory. It lets you experience continuity, duration.
So this is how we perceive an object as enduring. That the chair I'm looking at is the same chair from second to second, even if I blink or the light changes slightly.
Precisely. Without this reproductive synthesis, experience would shatter into disconnected instants. There'd be no flow, no enduring objects, just flickering data.
Okay, apprehended, reproduced over time. Now we need to make it objective, right? To say this isn't just my fleeting impression, this is actually a house.
That's the final step, the synthesis of recognition in a concept. Here, the unified and enduring intuition gets brought under one of the a priori categories of the understanding. These are the fundamental, pure concepts like substance, thingness, causality, cause and effect, unity, plurality.
These categories are like the highest level organizing principles.
They are the logical functions necessary for thought itself. Applying a category like substance to the synthesized intuition of the chair is what gives it objective validity. It says, this isn't just a subjective bundle of sensations, it's a stable, unified object that exists according to universal rules. It turns perception into judgment, into knowledge.
So putting it all together, if we think about this from a modern, maybe computational perspective, Kant's whole system is designed to solve what we'd now call an inverse problem.
Absolutely. That's a fantastic way to frame it. The mind receives these ambiguous, incomplete sensory effects, the 2D patterns on the retina, the sound waves hitting the eardrum, and it has to infer the most likely stable underlying cause, the 3D objects and events in the phenomenal world.
And since the ultimate cause, the noumenal world, is hidden, the mind has to impose its own structure.
It has no choice. It uses its built-in rules, the forms of sensibility, space, time, and the categories, substance, causality, etc., to construct the best, most coherent, most predictive model of reality possible from the available sensory data. The imagination synthesis is that active inference process.
That is just incredibly prescient. A philosophical blueprint for an active, constructing, predicting mind laid out in the 18th century.
And it sets the stage perfectly for where neuroscience eventually picked up this thread centuries later.
Right. Let's pivot to that. Fast forward a couple hundred years, neuroscientists start talking about the Bayesian brain hypothesis. How does that connect?
Well, the connection is striking. The Bayesian brain idea basically says the brain isn't just processing information, it's fundamentally an inference machine. It operates probabilistically, constantly making bets about the state of the world based on sensory evidence and its prior beliefs.
It's trying to figure out the hidden causes of its sensations, just like Kant's mind.
Exactly the same problem. And the most influential, mechanistically detailed version of this idea is predictive coding, or PC.
Predictive coding. Okay, tell us the core idea there.
The core idea is that the brain isn't a passive sponge soaking up data. It's an active prediction engine. It has an internal, hierarchical generative model, basically. A sophisticated, multi-layered representation of how it thinks the world works, built up from past experience.
Hierarchical meaning different levels of abstraction.
Yes. Higher levels in the cortical hierarchy represent more abstract concepts like face or dog. These higher levels generate top-down predictions about what sensory signals the lower levels should be receiving if that concept is present.
So my brain is constantly guessing. If there's a dog in front of me, I predict I'll see these shapes, these textures, maybe hear this kind of sound.
Precisely.
Oh.
These top-down predictions cascade down the hierarchy, becoming more and more specific until they reach the earliest sensory areas, predicting the actual patterns of light on your retina or vibrations in your cochlea.
Okay, so the brain is predicting. What happens when the prediction meets reality?
That's where the action is. The brain compares its prediction to the actual incoming bottom-up sensory signal. Any mismatch between the prediction and the signal generates a prediction error.
The error signal. That sounds crucial.
It's the engine driving the whole system. The prediction error is basically the brain saying, whoa, what I'm actually sensing doesn't quite match what I expected. This error signal is then passed back up the hierarchy.
To do what?
To update the model. The error signal tells the higher levels, your prediction was off, adjust your model to make a better prediction next time. The fundamental goal of the brain, in this view, is to minimize prediction error over time. Minimize surprise.
It wants its internal model to match the world as closely as possible. Now, our sources mention two main ways the brain can reduce this error.
Yes, and this is where agency comes in. The first way is perceptual inference. If there's prediction error, the brain can adjust the connections, the weights, within its internal generative model to make its future predictions more accurate.
That's learning, basically. Changing my beliefs to fit the world. I see something unexpected, and I update my mental model.
Exactly. But there's a second, equally important way. Active inference.
Active inference. This sounds more proactive.
It is.
Yeah.
Instead of just changing its internal model to fit the sensory input, the brain can initiate actions to change the sensory input itself so that it better matches the existing prediction.
Can you give an example?
Sure. Imagine you're in a dark room and you predict your keys are on the table. You reach out, but your hand encounters nothing. Prediction error. Now, you could just update your model. Okay, keys aren't there. That's perceptual inference. Or you can engage in active inference. You keep your prediction, keys are on the table, but act to gather more confirming sensory evidence. You move your hand around, maybe turn on the light. You're actively changing the incoming data stream to try and make it conform to your prediction.
Okay. So it's changing the world to fit your beliefs, or changing your beliefs to fit the world, and the brain is constantly balancing these two.
Constantly. And how it balances them depends crucially on something called precision weighting.
Precision, like how reliable the signal is.
Exactly. Precision is the brain's estimate of the certainty or reliability of the prediction error signal. If the sensory input is clear and unambiguous, high precision, the brain gives that error signal a lot of weight. It strongly updates its model, perceptual inference.
But if the input is noisy or ambiguous, like in that dark room,
Then the sensory input has low precision. The brain downweights the unreliable error signal and relies more heavily on its existing top-down predictions, its priors. This precision weighting mechanism is thought to be the neural basis of attention. We attend to signals we deem reliable.
that makes sense. You trust your eyes more in bright light than in fog.
Right. And this has implications for things like confirmation bias or even more severe conditions. If sensory precision is chronically low, or if top-down priors become pathologically strong, the internal prediction can start to overwhelm reality. The model doesn't update properly based on evidence.
Wow. Okay, so it's a really dynamic system, and it seems to dissolve the old distinction between perception and action.
Completely. In the active inference framework, action isn't something that happens after perception and decision. Action is a form of inference. Motor commands are essentially predictions about proprioceptive feedback, the sense of your body's position.
So to lift my coffee cup, my brain predicts the sensory state of cup successfully lifted, and then my muscles move to fulfill that prediction.
That's the idea. The brain predicts the sensory consequences of the movement, and the reflexes act to minimize the error between the predicted and actual bodily state. Perception and action become two sides of the same coin, minimizing prediction error to maintain a stable, predictable relationship with the world.
Okay, the parallels with Kant are starting to feel uncanny now.
They are incredibly deep.
Yeah.
Many people in the field explicitly see predictive coding as a kind of neurocomputational implementation of Kantian principles.
Especially the methodology, right? That reverse engineering approach you mentioned.
Absolutely. Kant used his transcendental method. Start with the undeniable fact of our coherent experience, synthetic a priori judgments possible, and reason backward to figure out the necessary preconditions in the mind. Forms, categories, synthesis.
And PC theorists do something similar.
Very similar. They start with the known abilities of the brain, like how quickly we recognize objects under noisy conditions, and ask, what kind of computational architecture must the brain possess to do this? The answer they arrive at is this hierarchical prediction error minimizing system. Both start with the what and deduce the how.
And both are fundamentally trying to solve that inverse problem, getting from ambiguous sensory effects back to their hidden causes.
Yes. Whether you call the hidden cause the noumenon Kant or the distal stimulus in the environment, neuroscience, the problem is the same. And the solution, radically, is that perception isn't a passive reflection of reality. It's an active construction, a controlled hallucination, as some put it.
We perceive our brain's best guess, constantly corrected by error signals.
Precisely. Let's make the mapping really explicit for everyone listening. This is where it clicks.
Okay, let's line them up. Kant's engine of construction.
That's the synthesis of imagination. The active process taking raw data and building a coherent percept. Its direct functional parallel in PC is the generative model. Both break the gap between abstract concepts and raw input, imposing structure and creating order.
Got it. Synthesis of imagination maps to the generative model. What about the fundamental rules, the bedrock?
For Kant, those are the a priori categories, substance, causality, unity, etc. The non-negotiable rules for objective thought. In PC, these correspond remarkably well to the high-level, deeply ingrained Bayesian hyperpriors within the generative model.
Priors being the brain's built-in assumptions about how the world generally works.
Exactly. Assumptions like objects tend to persist, causes precede effects, the world is generally stable. These abstract priors aren't learned from scratch with every experience. They provide the fundamental constraints that make learning and inference possible in the first place. They are the rules of the game.
Okay, categories map to priors. And the final piece, the reality check, the thing that stops it from being pure fantasy.
For Kant, concepts need empirical content. Intuitions need conceptual structure. In PC, the mechanism for this is the prediction error. It is the empirical content, the signal from the world that pushes back against the brain's hypotheses.
So prediction error forces the generative model, the concepts, to stay grounded in the sensory input, the intuitions.
Perfectly put. Without prediction error, the generative model would just be spinning fantasies, unconstrained by reality Kant's empty concepts. The error signal is what ensures the model stays coupled to the world, constantly updating and refining itself.
That mapping is incredibly compelling. Kant's philosophy provides the why and the what, and predictive coding provides a plausible how.
It really feels like a convergence across centuries and disciplines. But now, we need to introduce the third player in this story, the large language model.
Right, the AI prediction engines that are dominating headlines. Superficially, they're also all about prediction.
They are. But the kind of prediction and the underlying architecture is where things get really interesting and where the analogy starts to diverge significantly from the brain.
Okay, so what is the fundamental task of an LLM?
At its absolute core, it's incredibly simple, almost deceptively so. Next token prediction. Given a sequence of text units, or tokens, predict the statistically most likely token to come next.
Tokens are like words or parts of words.
Yeah, usually subword units. The text gets broken down, tokenization, and each unique token gets mapped to a high-dimensional vector at a point in mathematical space. This is its embedding.
And the position in that embedding space captures meaning.
It captures relationships based on context. Tokens that appear in similar linguistic context in the training data end up close together in the embedding space. Dog will be closer to puppy and bone than it is to car or philosophy.
Okay, so text becomes numbers in a meaningful space. Then how does it predict the next token? That's the transformer architecture, right?
Right. The big breakthrough was the transformer, and specifically its self-attention mechanism. Older models tried to process text sequentially, which made it hard to track long-range dependencies.
Like remembering the subject of sentence paragraphs later.
Exactly. Self-attention allows the model to look in the entire input sequence simultaneously. For each token position it's trying to predict, it can dynamically calculate how relevant every other token in the input is to making that prediction.
So it can weigh the importance of context, near and far. If I say, I went to the bank to deposit, it pays attention to deposit to predict money rather than river.
Precisely. It calculates these attention scores across the whole input, allowing it to capture complex long-range context incredibly effectively. It then uses this context to generate a probability distribution over its entire vocabulary for what the next token should be, picks the most likely one, or samples from the distribution, adds it to the sequence, and repeats.
Okay, so it's a statistical pattern matching machine, predicting the next piece of text. This leads to that stochastic parrot critique, just mimicking patterns without understanding.
That critique exists, yes. But the counter-argument, which is compelling, is that to become really, really good at next token prediction on a massive, diverse data set like the internet, the model must implicitly learn an enormous amount about the structure of the world as reflected in language.
It has to learn grammar, facts, patterns of reasoning.
Even things that look like social understanding or theory of mind. Why? Because predicting human language often requires predicting how humans reason about each other's mental states. These complex abilities seem to emerge as a side effect of optimizing for that simple prediction objective.
So the LLM builds a kind of generative model, but it's a model of language use, which is itself a reflection of the world.
It's a model of the statistical patterns in text generated by humans interacting with the world. That's a crucial distinction we need to hold on to. It's predicting text, not directly predicting sensory input from a physical environment.
Okay, that feels like a key point leading into the differences. While both the brain under PC and LLMs are prediction engines, their architectures and how they learn are fundamentally different.
Massively different. Let's start with learning and updating. The brain, PC, as we said, uses continuous online learning. It's constantly adjusting its synapses in real time based on incoming prediction errors. It learns incrementally from every single experience.
It's always adapting.
Always. The LLM, in contrast, uses offline batch processing. It learns pretty much everything during a gigantic one-off training phase on a static dataset. After training, its core knowledge, its weights, are essentially frozen.
So talking to ChatGPT doesn't actually teach ChatGPT anything new in a fundamental way.
Not in the way your brain learns. It doesn't update its core model based on your conversation. Any appearance of learning within a chat session is usually about maintaining context within that session, or perhaps fine-tuning on curated data later. But it's not the continuous real-time synaptic plasticity we see in the brain. Updating an LLM's core knowledge requires massive retraining.
Okay, learning is different. What about how information flows?
Also very different. The brain, PC architecture, is inherently bidirectional and recurrent. You have that constant loop. Top-down predictions meeting bottom-up sensory signals, generating error signals that flow back up to correct the predictions. It's a dynamic equilibrium.
A continuous dialogue between expectation and reality.
Exactly.
Yeah.
LLMs, particularly the transformer architecture, are primarily feed-forward and autoregressive. Information generally flows in one direction, from the input prompt through the layers to calculating the probability of the next token. While attention looks backwards at the input, it lacks that continuous hierarchical cascade of prediction and error correction flowing in both directions simultaneously that defines PC.
It's more like a production line for the next token, rather than a system constantly checking its world model against incoming reality.
That's a good way to put it. And this ties into their relationship with Bayesian inference. PC is explicitly designed as a plausible way the brain could approximate optimal Bayesian inference, updating beliefs rationally based on evidence.
LLMs use probability, but are they truly Bayesian?
They are probabilistic machines, yes, but they're optimized to minimize a specific cost function related to text prediction accuracy, like cross-entropy. They aren't necessarily optimizing for maintaining a coherent, probabilistically sound model of the world in the same way a Bayesian agent theoretically should. They can and do violate principles of optimal Bayesian updating because their goal is fluent text generation, not necessarily truthful world modeling.
So, boiling it down, Different learning, different information flow, different optimization goals. It sounds like they're built for fundamentally different purposes.
I think that's the clearest way to see it.
Yeah.
The LLM's purpose is generation. Its entire architecture is honed to efficiently produce statistically plausible sequences of text. Its predictions serve the goal of creating coherent output.
And the brain's purpose.
The brain's purpose, under PC, is inference and action for survival. It needs to build and constantly update a robust, dynamic, causal model of its environment to guide behavior, find resources, avoid threats, and maintain its own internal balance. Homeostasis. Its predictions serve the agent acting within the world.
That distinction, predicting for text versus predicting for action in the world, feels like the crux of the matter.
It really is. And it leads directly to the biggest, most glaring difference.
Yeah.
The LLM has no body.
Right. The sheer lack of embodiment, no sensors touching the world, no limbs to act upon it. How critical is that?
It's arguably the most critical limitation, and it brings us right back to philosophy, specifically the grounding problem. How do symbols, like words, get their meaning?
For us, meaning seems tied to experience, right?
Exactly. For an embodied agent like us, the word apple is grounded in a rich network of non-linguistic sensoromotor experiences. What it looks like, feels like, tastes like, the motor actions involved in picking or eating it. Language is anchored in the physical reality we interact with.
But for an LLM,
Meaning is purely relational, defined by statistical co-occurrence within its text data. Apple means the cloud of other tokens. It frequently appears alongside red, fruit, tree, pie, Newton. It's a vast web of symbols pointing only to other symbols. It's unanchored, ungrounded in physical experience.
a closed loop of text.
A closed loop. And this lack of grounding is why, although LLMs can manipulate linguistic patterns related to causality incredibly well, they lack genuine causal understanding. They learn correlations, not causation.
They know smoke and fire appear together often, but don't understand the actual physical process?
Precisely. They learn that sentences expressing causal links follow certain patterns, but because they don't experience the interventions and consequences in the real world, their grasp is brittle.
This explains their brittleness, why they can fail on seemingly simple variations of problems they seem to understand.
Yes. They might correctly answer, who is Tom Cruise's mother? Because that specific factoid is likely stated explicitly many times in the training data. Strong correlation. But ask the inverse, who is Mary Lee Pfeiffer's son? If that precise phrasing is less common, the model might fail because it hasn't built a robust, reciprocal, causal model of family relationships. It just matched a pattern.
It learned a statistical shortcut, not the underlying structure.
Exactly.
Yeah.
And we see this in more complex tasks too, like those simulated city navigation studies you mentioned earlier. The LLM learns the route from the training data. But if you block a key street, not blocked in the training, a novel intervention, if performance collapses because it doesn't have a causal spatial understanding of why rights work or what alternatives exist, it just knew the statistically likely path from the data. Its world model is fragile and often incoherent when perturbed.
This brings us back to those foundational structures, Kant's categories, Bayesian priors, and whatever corresponds in an LLM. It seems really dangerous to just treat them as equivalent.
It's a fundamental error. We need to be crystal clear about the differences in their origin, function, and malleability.
Okay, let's break it down. Kantian a priori categories.
Origin. Innate, or at least transcendentally necessary, required for the very possibility of objective experience. Malleability. Absolutely fixed. They don't update with experience. They structure experience, function, to constitute objectivity itself.
Okay, foundational, fixed, constitutive. How about Bayesian hyperpriors in the brain?
Origin. Can be innate, evolutionary, learned early or even assumed. They are initial beliefs or structural assumptions. Malleability. Critically, they are designed to be updated by evidence via Bayesian conditionalization. They are refined by experience. Function. To constrain inference initially, but to be shaped by data over time.
So potentially innate, but definitely updatable and empirical, and LLM learned by priors.
Origin. Purely statistical artifacts of the patterns and biases present in the training data. They reflect human language use, warts and all. Malleability. Static after training. Updating requires massive retraining. Function. Solely to improve the statistical prediction of the next token, enabling plausible text generation.
They're not about modeling reality accurately, just predicting text patterns accurately.
Precisely. So confusing these three is a major category error. You're conflating a system that makes objective experience possible, Kant, a system that learns a causal model of the objective world, PC brain, and a system that mimics the statistical patterns of language describing that world, LLM. Very different things.
That clarification is incredibly helpful. It really delineates the landscape.
So we've traced this amazing arc. Kant gives us the philosophical necessity of an active constructing mind. Predictive processing offers a plausible biological mechanism for how that construction and prediction might happen in the brain.
And the LLM. It comes along as this powerful demonstration of what pure statistical prediction can achieve with language.
But also, crucially, it serves as an invaluable scientific foil. Its successes highlight the power of prediction, but its failures, the lack of grounding, the brittleness, the incoherent world models starkly reveal what's missing for true general intelligence.
It shows us that prediction, while maybe necessary, is definitely not sufficient.
Exactly. You need prediction plus embodiment, plus grounding through sensor-motor interaction, plus the ability to build and refine a robust causal model geared towards action in the world, not just text generation.
It brings us right back to Kant's core insight, doesn't it?
It really does. Concepts without intuitions are empty. The LLM has concepts, patterns, and text, but lacks the grounding intuitions, sensor-motor experience, and intuitions without concepts are blind. Raw sense data without the structuring concepts, categories, priors, would be chaos. You need both integrated.
A powerful synthesis of centuries of thought.
Yeah.
But there's still something left out, isn't there? Even if we built an embodied, predictive, causal AI.
Yes. The elephant in the room, consciousness. The subjective, qualitative feel of experience, the what it's like.
These models, Kant's philosophy, predictive coding, even future embodied AI, they describe the function, the mechanism of cognition and perception.
But they remain largely silent on how or why that physical processing should give rise to subjective awareness, the inner light. That remains perhaps the final frontier, the deepest mystery that bridges philosophy and science.
Something for us all to keep pondering. Well, this has been a fascinating journey through some really deep connections.
It really ties together so much. If you, listening, found this exploration as stimulating as we did, please do consider liking this episode, subscribing to AI History of Western Philosophy, or maybe leaving us a comment with your thoughts.
Your engagement really does help us keep digging into these intersections of ideas and technology. Thanks so much for joining us for this deep dive into the prediction machine. We'll see you next time.